the case one we just talk about is interstitial charge ions in ionic conductors, and these interstitials actually serve as play an important role in current density in ionic conductors, right? And next we are going to talk about, instead of the ionic conductor, we talk about the metals. And the one we interesting in here would be the atoms, the interstitial or substitutional atoms in metals. Okay, so this is we call the mass transport under, also the mass transport under electrical field, but it's in metals. So usually people call it electron migration part. Usually they are emphasized in the metals. Why? Because actually the situation will be slightly different here. What we have here is we have metal ions shown in gray circles, or gray gray circles here. And when I apply or connect these materials to a battery to apply the electrical field, the direction will be to your left-handed side. Left-handed side. That tell you the current will also go to your left-handed side. So electrons flow will go to your right-handed side. So what is the electron migration? When you apply the electrical potential gradient, induce diffusion in metals, and due to why that will induce the atomic diffusions in metals due to the cross effect between the diffusions at species and also the flux of the conducting electrons through the momentum exchange between the electrons flow and also the metal ions here. So what this means actually is, for this case, as long as, because we apply to the battery or connect to a battery, as long as we do have the large electrons flow, which bombardment on your metal ions, as long as this bombardment or this flow is high enough, it have chance to move, to drive this atoms moves. And as long as this metal ions moves, then that it will left a vacancy here. So this is we call the electron migration. Like due to the electrons flow induce atomic migration. So in this slide, usually people won't talk about this phenomena is electron migration. It is just you apply the electrical field acting on your ionic conductors. But in this case, people usually call it as electron migration because this migration is due to electrons flow. But it only happens on you have a large enough current density or electrons flow. Okay. So as I mentioned before, some scientists observe this phenomena, this weird, in the beginning, they call it as a weird phenomenon because they find that the positive metal ion moves toward to anode instead of cathode. So this is, in the beginning, they find it's quite weird. So they perform more experiments to investigate why cause this phenomenon happens. So they find that as long as the current density increase, and they can observe more metal ions moves toward to anode. So this is how it be developed or be discovered. And why this electron migration is so important? During the semiconductor industry or inside your device, when you try to etch away the dielectric insulation layers, and you will observe the copper conducting wire below, right? And below this conducting wire, we can see at the bottom that this is the transistors. And this is copper wire, iron conducting wire. So if you take a cross-section point of view and investigate these copper wires under the SEM scanning electron microscope and take some pictures, and I also highlight the direction of electrons flow is go to left-handed side and move to upward, then go to left-handed side. And what we have here is this wire is made of copper, but we observe some void. You can see one void here, some void here, some void here. And also we have some crack void space here inside this conducting wire. So as long as the electron migration happens, which means that each migrating atoms will leave its vacancy, and this vacancy, as long as they get together, they will form some void, and this voids get larger and larger, cover, as long as it cover a whole wire, a whole line, it turns out open to this circuit will turn out to open, and this device will fail. So this is why very important, because under the under the semiconductor industry, they always like try to decrease the line width. That will lead the current density dramatic increase. In the meantime, the electrons flow increase as well. So that will lead, you will have more and more void formation inside this conducting wire. So that definitely will cause, that probably because you got lots of void, so the reliability of this device will be effect. So this is why this EM is so important. How to avoid this void formation is become the crucial issues in um, in semiconductor industry, especially when you design your conducting wire. OK，所以在这里的话，嗯，通常我们就只会大部分大家讲说 electron migration，通常会讲的这个 term，通常会比较多讨论的会是金属，像前面的这个呃就是离子材料的话，我们最多就说这个离子材料基本上我们帮它添加上电场之后发生了一些事，那我们就可以透过这里知道它的 conductivity 事实上是被什么决定，这些 dopant 的什么条件决定。所以 electron migration 它对于半导体元件的导线来讲，事实上是不好的。但随着线宽追求越来越小，然后你的 current density 会以指数的方式上升，那我的 electrons flow 也会大幅上升的前提之下，electron migration 就变成是不可避免的问题。那如何让它变小，或者是有没有其他的一些方式，就是我们就是一些设计导线的人需要 address，他需要解决的一个现在很棘手的一个问题，因为这很明显会，如大家知道，只要这个 void cover 这整个 wire， 这整个 device 就 fail 了，就变成 open circuit， 所以这就蛮严重的。But how to quantitatively analyze the atomic flux, or I can say in terms of that, how much void be generated during this electron migration? Okay, so we want to show you how to quantitatively estimate that. So I'm also give you an example here. And what we have here is we have a metal, and we consider there's a dilute solvent solutions of interstitial atoms, which means that and you also under electrical field at constant temperature. So also we have a metal ions, and the example of the figure I draw here is FCC. We have a host atom, is FCC structures in FCC structures, and we have a dilute solvent at interstitial site, showing red here is a solute atom here. And when I connect these materials to the battery, I'll apply an electrical field on it, and I hope you can write down the current density and also the atomic flux for these interstitials. And there are two possible driving forces. So based on the flux force equations, we have chemical potential gradient to driven the to contribute the current density and also the interstitial atomic flux. And the second possible driving force here is the electrical field are acting or I connect to this material, so the second driving force. And directly driven by the contribute the current density and indirect also affect or contribute some interstitial atomic flux. And as I mentioned before, actually, I want to investigate the void generation rate. I'm more interested on interstitial atomic flux because this I can get the void generation rate. So I just put this current density part here and equals to almost low. Okay, so just leave it here. I'm not going to use this for further calculation or something. So, but I'm going to put more efforts on interstitial atomic flux. I want to know what is the magnitude for interstitial atomic flux. Then I can know the vacancy flux, right? Okay, so if you take carefully for the interstitial atomic flux, one is this one. It's directly driven by the negative chemical potential gradient and indirectly driven by the electrical field I acting on these materials. Okay, so let's put so next I'm going to emphasize on this term, indirect term, and use the symbol we use the atomic flux, interstitial atomic flux, and small e means that induced by the electrical electrons flow or electrical field. Okay, so this write down this as a vectors of this atomic interstitial atomic flux driven by the electrons flow. This flow, you can image that why these interstitials can move through these materials under electrical field. Why? Why? There are how many driving force acting on it due to the electrical field part. So if you have no idea at this moment, so probably you can just simply write down the atomic flux induced by the electrical field or electrical field would be expressed as like a mobility, concentration, and driving force. And this driving force is related to the electrical field, right? So mobility can be rewritten as the facility divided by kT. And concentration I read here. And the electrical field, or the driving force acting on these interstitials, we write that as a beta E. It's not that difficult to understand why we write down as a beta E. F is a QE, right? Q times the negative QE or Q times the negative electrical potential gradient. So driving force, so we have, but here instead of QE, I use the beta. Beta, people call it as effective charge of the diffusing atoms. Because I have no idea what exactly the charge it carried on these metal ions. But people will probably say, Professor, why you have no idea? Because if you take a look on this positive interstitial atoms, how many driving force co-acting on it regarding to the electrical field? The first thing is when I apply the electrical field on it, actually it will have the field, right? One driving force due to the electrical field I apply on these materials. But however, besides this one, in addition to this electrical field, this interstitial also have the other, also there's the other driving force, which is what? The electrons win or electrons flow will push this positive interstitials toward to anode. Because if this is anode, this is the cathode, so the current will be go this way. So electrons flow will go right, the upside direction, go to right-handed side. So if you take a closely look on how many driving force acting on this interstitial, positive interstitial, there are two. One is electrical field you acting on it, and the other is electrons flow or bombardment on these metal ions, and probably will be push it toward to anode. So we need to sum them together and we will get the final exactly effective driving force. So under this situation, we have no idea what it would be. So we use a beta. People call it as effective charge. And we have chance to measure what is beta. Okay? And under some situations, if we do not have large electrons flow, but then these atoms, which means that this is small, so these atoms, interstitial positive atoms, probably have chance to go to left-handed side. But if the electrons flow will be large enough, then this will be larger than electrical field. The force due to the electrical field. So the interstitials probably will move toward to right-handed side, which is the same moving direction with the electrons flow. So as long as you find that the beta is negative, which means that this interstitials moves the same direction with electrons flow. Okay. So as we mentioned, the sign for this beta can tell you the moving directions of these interstitials. And by the way, you also have some people, by the way, this is not that important, but some people probably were curious about what is L1Q, this coupling coefficient. Based on this, you delete Z, so you can get this divided by KT. This is L1Q. It's not that important, but some people probably were curious about what's the L1Q. Okay. Okay, so due to you already write down this term, so I just want to sum them together. So what's the total interstitial atomic flux? The first term is driven by the chemical potential gradient, as we mentioned before, will obey Fick's first law, will be negative diffusivity of these interstitials times the concentration gradient of these interstitials. And the second term will be this term, will be mobility concentration driving force. So I write down. So will be the mobility, negative is positive, right? Mobility. Mobility is D divided by KT. Mobility concentration and also the driving force is beta E. Okay. Mobility, concentration, and driving force. So this is the total interstitial atomic flux. In order to simplify them, if you visualize like dilute solution, also tell you that the concentration of this interstitials is quite small. So you can delete this term. So you can use this mobility concentration and driving force to estimate the interstitial atomic flux. So now you already know what is the interstitial atomic flux, which is this, right? But now still one parameters you have no idea which will be, because diffusivity you can measure them or find the the roughly diffusivity from the literature, right? KTT is working temperature, E is the electrical field you acting on this, and concentration you can measure because you dope, right? This dopant. So, but the beta you have no idea what's a beta. So next, next we need to know the beta, then put it back, then I can get the atomic flux. So how to measure the beta will be the most important part here. So we use this slide to show you how to determine the magnitude and also of the beta. Okay, how to determine the beta? You need to design these experiments and perform these experiments for your samples, your interesting samples, then you can determine the beta by yourself. So what we have here is we have, in beginning, I have one materials with constant interstitials, constant concentration of interstitials. Then next, I acting electrical field on these materials, and the direction is moved to left-handed side, which means that you got the anode on your right-handed side. You connect the anode on your right-handed side and cathode on your left-handed side. And we have a electrical potential gradient go this way. So we have a current go to your left-handed side. Current, okay? Go to your left-handed side. So electrons flow will go to right-handed side because it's opposite direction of the current. So electrons flow will go right-handed side. So as long as electron flow is high enough, so it will go to push this interstitial atoms. So the concentration will be push some atoms to move to right-handed side. So we will have lower concentration at left-handed side and higher on your right-handed side because I push atoms, interstitial atoms toward to right-handed side. So I will have higher concentration on right-handed side. So this is, we push that, so mobility, concentration, and driving force. And as you know, as long as concentration is, we have concentration variation, the fixed first law will be come out to compete or to balance this flux. So we do have a fixed first law. As long as we do have a concentration gradient variation, the fixed first law will be come out to balance this flux. So now we have the two atomic flux with opposite directions. So as long as it reaches quasi steady state, which means that the net flux equals to 0, which means that the magnitude, this equals to this. Okay, because as long as this equals to this, then net flux equals to 0. So how can I know this flux induced by the electrons flow or electrical potential gradient equals to the fixed first law? We find that as long as we find this concentration profile does not change with time, which means that no net mass transport. Under these situations, the value, I mean, this is the magnitude. So this equals to this. So I can get beta. So the beta will be like this, and I just substitute E as J equals to low E. So I use E to have like this. So I can, as long as system reach quasi steady state, then I can use this to determine the beta. So temperature, I know. The conductivity of this material, I know. Concentration gradient, I can measure that. And concentration of this interstitial, yes, and current density for sure can be measured. So I can, under this situation, I can determine the magnitude of the beta and also the sign, positive or negative for this one. So the experiment idea will be, you can like, in order to check whether the system reach quasi steady state or not. So as long as you can like, you can choose 3 different time points and do a section and do the analyze to plot this concentration profile to check whether the concentration profile change with time or not. Then you know that whether this E, this electrical field you acting or apply on this system can whether this allow system to reach steady state or not. Okay. Okay, so this is how we get the, as long as you determine the beta, then you can use this beta back, then you can get this atomic interstitial atomic flux. So this is whole story. But be honest, if you ask me, professor, it turns out reasonable, but how how to perform these experiments step by step? Okay, so usually we'll go this way. Because the only parameter we have no idea will be the magnitude for electrical field, right? So people usually were starting from the lowest one and slowly try to increase the electrical field to check whether the system go to quasi steady state or not. So starting from lowest electrical field and wait for 3 different time point to check whether concentration profile change or not. If it changes, which imply that the system have does not haven't reached quasi steady state, then you need to slightly increase the electrical field. Then do the same procedure. Choose like 3 different time points and section them and plot the concentration profile and to check whether this profile change with time or not until it reach you find the specific electrical field that allow the system reach quasi steady state. Okay, so this is like for your reference. Now we move to the pure metals. So I use the circles to represent the metal ions or positive metal ions we have in pure metals. So we also connect to the battery, and we have the anode here and cathode here. We connect to a battery. And after I connect to a battery, you can expect that this positive metal ions will move to left-handed side because it's positive charge, right? And due to the internal electrical field, it will prefer to move to cathode. But however, as long as the current increase, then probably that will, as the current increase, then that means that you also have a higher electrical field, electron flow. Move to the current will go this way, right? But the electron flow will move to the opposite direction, move to right-handed side. So we have the atomic flow or atomic flux induced by electrons flow. We use the IE to represent it. So here we want to know here in this case, we also want to know understand the atomic flux inside this pure metals. So as we mentioned before, in pure metals, we only have 2 components, the atoms or the vacancy. But how this atom moves inside this pure metals? The only possible actually is exchange the location with surrounding vacancy. For example, like there's blue atoms, they can make a left jump to exchange with a location with this vacancy. So these atoms can move to left-handed side, right? So this is how they moves inside this, how the atoms moves in the pure metals. But in order to answer the atomic flux, you don't forget the relationship between the atomic flux and the vacancy. The total net flux should equals to 0. So the only flux we have here is the atomic flux and the vacancy flux. So this plus this equals to 0. So in order to know the magnitude and direction, moving direction of atomic flux, either you measure this directly, or you can measure the atomic the vacancy flux, right? either way should be okay. So when we try to, and there are two approaches, right? Either you directly measure the atomic flux, but however, this system is pure metals. Each atoms are the same. Even though this atom move to left-hand side, any material analyzed tool is cannot uh, detect this tiny concentration change for this in this pure metals because all of them are the same, right? So this is quite difficult to us to directly measure the atomic flow for atom A. So on the other hand, probably we have chance to measure the vacancy flux. So because as long as you have a vacancy flux, probably you can visualize them in like void formation, the form like the voice, small voice, large voice. And as long as you have you visualize the void, you can estimate the volume for this void. So this is how we um, get or analyze all the magnitude for the vacancy flux. So in order, because we cannot directly measure JA, so we use a JV instead. How to express the vacancy flux? The same idea, how many possible driving force acting on this vacancy or on the atoms. So probably the vacancy flux can be driven, probably in the system, they have a vacancy, I mean concentration gradient for vacancy. So we write down the JVC, which also the same with the chemical potential gradient, serving as a driving force to drive the vacancy flux. And because we connect to the battery to provide the electrical field, so the local electrical field or electromigration probably also contribute or affect the vacancy flux. So we write down these two flux driven by two possible driving force. And for the first one, concentration gradient, if you take a look on the lecture notes, you can also write down like a concentration gradient actually is a chemical potential gradient. So you also can write down like show like equals to coupling coefficient, driving force is negative chemical potential gradient, and also the other coupling coefficient and driven by electrical field. You just connect to. Okay, so we take a look carefully here. As long as in the pure metals, the chemical potential gradient, usually people will use to minus the UV, chemical potential of vacancy, to serve as a driving force here. As long as you just have two components. And in order to know the chemical potential difference when you have a pure metals or you have a system with the atoms and the vacancy. So we write down the chemical potential of atom A, and in this material system, we do have some vacancy inside. So after series, this is how we get the chemical potential of atom A, right? In this system with a vacancy. And we have the mu A0, which is the chemical potential of atom A in pure A material without vacancy, plus the KT log NA, numbers of atom A divided by the total atoms, included the atom and vacancy. And as you know, the numbers of vacancy usually is much smaller than the atoms. So this term you can almost log 1, right? You can ignore this term. So you got the mu A equals to mu A0. Also imply that even now the system, there are some vacancy inside this pure metal systems. The chemical potential of atom A actually is the same with the pure one, the chemical potential of atom A in pure metals without vacancy. So it's also implied that we don't have chemical potential gradient of atom A in these systems. So we can simplify these results to delete these terms. So the vacancy flux directly influence or if of effect by the electrical field you acting or acting on the system. So this is one like explanation for why we can ignore this term. But the other point of view, like some people probably will uh, say that actually there's lots of vacancy sink inside the material system. The vacancy sink, which means that um, there are lots of dislocations exist in our material system, and this dislocations always absorb the vacancy. So they don't think there's really a concentration variation on vacancy. So the concentration of vacancy are uniform everywhere inside the material system. So this term, JVC, usually people don't believe we do really do have a vacancy flux. You cannot really visualize the vacancy flux passing through your materials. So based on this result, this idea, so can consider local equilibrium, or also assume we have a local equilibrium conditions. The chemical potential of vacancy should be constant, which means that we do not have the um, we don't have any like chemical potential vacancy. I mean, the chemical potential of a vacancy are constant everywhere inside these materials. So the chemical potential, so mu V gradient equals to 0, which means that have the vacancy no matter at where they have the same chemical potential, mu V. So because we ignore this term, so in order to know the vacancy flux only driven by the local electrical field acting on this material system. So that would be much easier, right? So in order to know the vacancy flux, so vacancy flux actually, don't forget our purpose actually is know the atomic flux, but it's not easy to uh, directly measure the atomic flux in these pure metal material systems. So instead of this one, so we measure the JV. So the JV here directly driven by electrical field. Then we ignore the concentration gradient part. So due to this one, you can rewritten them as a flux, right? Mobility, concentration, and the driving force. This is how we always deal with this. So mobility of vacancy, concentration of vacancy, and also the driving force driven by the electrical field or battery you connect to. Okay, so mobility also can be expressed as a diffusivity divided by kT, mobility, concentration here, driving force here, because the driving force here is really drive the vacancy flux actually is some kind of EM, right? It's electrons flow. So here also the same idea with prior case. We use the beta VE. And beta here we label with vacancy. It's not the metal ion. So beta E. And the beta here actually, this is vacancy, right? The moving direction for vacancy is upside direction with atoms, the metal ions. So for sure, this term always should be positive, because for metal ion should be negative. Negative means the moving directions is identical, the same with the electrons flow, and the positive means that the moving directions for this vacancy actually is identical with the current. Positive means identical with the current. So it's it make things right, because the electrons, if you have a lots of, I mean, the high enough electrons flow, the metal ion will push the eight metal ion move to right-handed side. At this moment, the vacancy will be moved to left-handed side. the same moving direction with the current, so it should be positive. OK，所以在这里的话，原则上来讲，在纯的金属里面呢，因为它就只有，然后因为它只有两个元素，一个是原子，一个是 vacancy。那如果我把它加上电池，然后再让这个电池的 voltage 增加，让 current 很大的时候，那我怎么样可以知道在纯金属里面它呃原子移动多少呢 ？Atomic flux。那为什么要知道原子移动？因为在纯金属里面，它可能也会因为 EM 的效应来有一些 void。所以如果我知道atomic flux 的话，我就是可以知道 void formation。所以它是其实同一个概念。那唯一不同的跟前面不同的是，前面这个例子它是interstitial atom，that would be the other atom，that would be easy to analyze by like EPMA SIMS。但如果是 but this case，就是在这里的话，就是你可以想象全部原子都是同一种。例如说，假设铜原子好了，那铜原子本身在电场上面，就算它有移动好了，因为它的浓度非常高，你用材料分析的 EPMA 或者 SIMS 去看，其实你看不出它们真的有微小的变化。所以也是因为这样的原因，所以我们想知道的是这个，但可以有机会量到的其实是 JV。所以前面的概念，那 JV 接下来就会问说 JV 是由哪两个力所，就是你要知道 JV，那他就要找到 vacancy 身上有哪几个力，一样就是它既然是 vacancy，所以就有可能有 chemical potential 上面的不一样，跟有接 battery，所以就会是电场或电位差的部分，然后就写出这两个。那就是 chemical potential 这里就花了一些时间解释为什么它可以忽略这一项。然后最主要，刚刚有用英文讲过了。那最主要的概念就会是，因为在材料里面有很多 dislocation，所以 vacancy 其实都会被 dislocation 给抓住，所以不会真的有 vacancy 在里面真的流动，很长程 long distance 的 moving。所以这个可以。然后另外一种就是有两种说法，一种是这个说法，一种是 chemical potential，它算给你看说，其实在有 vacancy 的情况之下，它 A 原子的 chemical potential 其实是很小的，就其实是一样的，跟纯材料事实上纯的 A 原子事实上一样的，所以它其实没有什么 driving force。这两种解法都可以。那接下来只剩这个时候，你就一样用刚刚的技巧 mobility concentration 跟 driving force。那在这种有接电场的情况下，它的 driving force 就会是一样是贝塔一。那贝塔比较跟前面不一样，这个贝塔不是指的是金属离子在电场中移动像带了多少电荷那个贝塔，因为这里是 vacancy，所以 vacancy 的移动方向会跟金属是不一样的嘛，所以它这个会是正的。那通常就是它的值会跟这个值会跟金属刚好是同样的 magnitude but different sign， 因为它会是 vacancy 会往左移动嘛。当在这个系统里面的时候，那往左移动其实就是电流的方向，所以这个贝塔 V 一定是正的。那看这个金属是什么金属，那它的这个贝塔真的值就会跟贝塔 V 的那个 magnitude 会跟贝塔是一样的，只是 sign 不一样。好，那就是 for pure metal， 你就可以用这种方式来知道它的vacancy 的这 atomic flux。那其实 JV 你有办法知道吗？因为 JV 你就会到时候你就会算，透过这个方式你就可以知道vacancy flux 是多少，对不对？那 vacancy flux 单位时间、单位面积产生多少 vacancy，那就乘上它的平均体积，你就可以知道单位时间、单位面积形成的 void 的体积是多少。那你在 SEM 或哪里，你就有机会找到那个看到 void 的，你就会估算它的大小，所以这个有机会量到。但这里没有办法，但我们透过量这个知道这个，其实也是一个不错的做法。Okay, give you a quick summary here. When we talk about EM, electromigration, usually we talk about everything happen in the metal materials or alloy materials. So the case we introduced to you simply divided in two parts. The first one is you extra added some dopants at the interstitial side. Then in order to get this interstitial atomic flux, then you can get can be driven by two driving force. The first one is due to the chemical potential gradient, obey fixed first law, so it's negative diffusivity concentration gradient. And the second term actually is due to electrons flow. As long as electrons flow is high enough, under this situation, the electrons flow probably will push these metal ions to move inside this electrical field. So we have the mobility, concentration, and also driving force beta E. Okay, and for the one in pure metals, we only have the atoms and vacancy in this type of systems. In order to know the atomic flux, it's quite difficult to directly measure it, but we can analyze the vacancy flux through like visualize the volume of the void formed inside these materials. So also the mobility, concentration, driving force here. Driving force here is beta beta VE here. So as I mentioned, the sign for the beta actually tell us the moving directions for this is for the metal ions and this is for this vacancy. And next we should introduce the typical examples to some people probably will say drawbacks for this electron migration induced by this electron migration. We call the Black effect. And the secondary drawbacks we call the current crowding. So we move to the first one, Black effect. Black effect, some people also call it as a short stripe effect. What this means, actually, they say that there's no electron migration damage when this stripe line or length is below a critical value, critical length. Under this situation, you are not going to visualize the EM damage. This we call a Black effect or short stripe effect. So I'm going to give you an example here. What we have here is we have a molybdenum conducting line at the bottom. On the top of it, we have an alumina line. And we also, because both of them serve as a conducting wire, so should connect to the battery or power supply. And this is cathode, this is anode. So when you apply the current passing through these materials, the current will move to left-handed side, the current from anode to cathode. So the electrons flow will go to the opposite directions. And due to the conductivity of alumina is much higher than molybdenum, so the electrons flow will go like this at the inside the molybdenum, then go up and go through alumina line. So as long as this electrons flow high enough, if it's low, the electron flow is low, then nothing will be happen. But with you try to slowly increasing the electrons flow step by step, then as long as it reach certain conditions, then this electrons flow always put like this electrons flow push the atoms, right, and cause the atomic flux. This atomic flux is we call alumina atomic flux, atomic alumina flux, right? In the beginning, when the electrons flow is small, then this atomic flow is small as well. So it will induce the deformation in this materials, while this deformation remains within the elastic range. But however, as the electrons flow get higher or larger, then that will cause this atomic flow increase. Then this deformation process will go to plastic deformation range. So that will result this kind of extrusion. We call it permanent deformation happen. And in the meantime, if you observe this deformation or this atomic flux, which also means that we have a vacancy flux move to the opposite directions. So we have the this region, because this atomic flux, lots of atoms move to right-handed side, then they will cause we have the compressive region at right-handed side. And compared to this region, this you see the void formation part can be considered as a tension region. So on this aluminum line, we do have the compressive region, tensile region, which we call the electrical stress. This is a typical stress field acting on these materials. Okay, so in order to explain this extrusion, so this picture is not very clear, so I grabbed some figures from the typical articles and try to introduce to you. So this is one type of extrusion we call a helix. And also this is whiskers, also is one type of extrusion. This is this like the helix. One side you can observe the helix, and the other side probably you will see the void. Is due to the electron migration, and also whisker growth also is a typical sign for the electron migration phenomena happen on your electrical and conducting wire. And the other is we also have metal one at the bottom, metal two at the middle. You can see this is extrusion happen on the metal two, and also void form in the metal one. The same idea for this image, we can see visualize the void open side here in the metal one. So this, no matter it's a whisker growth, this whisker, or this helix, or this extrusion, when it happened in your conducting wire, they probably will cause the short circuit happen in your device. And in the meantime, usually you have extrusion. The other side, you will for sure you will have a void form in your conducting wire. Then that will lead the open circuit inside your device. So the reliability for this device will get worse and worse. So this is what we want to avoid. So based on this idea, we want to avoid this uh, this this electron migration induced failure. So the point will be back to here. The story here, as we learn that in beginning, we do have a electron flow passing through this orange conducting wire, but we find that as long as this wire, this orange conducting wire, get longer and longer, then the extrusion will get worse and worse. And on the other hand, if you observe the extrusion, then must accompany with the void formation at the other side. So this 2, 3, 4 is we don't want it at. So we want to calculate or estimate what is the minimum critical length, and that will and you are not going to visualize the EM damage for this conducting wire. This is what we want to design for our conducting wire in our device. So this is LC is what we are interested in, because as long as the line width, conducting line width is smaller than LC, then you are not going to visualize the EM induced failure or EM induced void formation and extrusion. So this is quite important, right? So we want to know the critical length in this short stripe. Okay, so in order to answer these questions, probably you need to write down the atomic flux, how many possible driving force acting to induce this atomic flux, right? So if you analyze this conducting line, how many driving force acting on it, because there's electrons flow passing through this material. So first thing come up from your mind will be, Professor, EM. So yes, atomic flux for sure will be driven by the electrical field you apply on this material system. So it will be mobility, concentration, and driving force beta E. Besides this one, there's the other possible driving force I explained to you before in prior slide is what? Is stress field, right? Stress field probably will also, as long as you push the atom move to right-handed side, then that induce the stress field. So stress field probably will counterbalance this atomic flux. So we also have the other possible counterbalance part, which induced by stress field. So we also write down the stress field induced this probably to counterbalance，就去抵挡这个 EM 的效果。因为你可以试想到说，这边的话，一开始，当电流推着原子往右的时候，那它左右两边的，只要它有一点点移动，那右边这里就会有慢慢的，它就有 compressive，对不对？那这边就会有 tension，所以这是另外一个它同时它 A 原子往右移的时候，然后的同时还会产生的一个力。那如同大家知道，一个材料它如果在初期的时候，如果它的形变量 deformation 事实上是 within elastic 弹性区间的话，其实这个材料还不会产生形变。当你把力移走时，它会恢复原来的样子。所以就是一开始其实是那样，但它超过它的弹性，变成 plastic deformation，所以它就会造成永久变形。所以在这里 the other possible driving force actually is also mobility concentration. Driving force here is a stress field. But how to formulate the driving force to represent the stress field? So driving force, usually I will think about force. Actually, it's a work divided by distance. So the work, this is work divided by distance. So how to formulate the work induced by stress field? So this is the stress. This is in the elastic regime, plastic deformation, elastic deformation, and plastic deformation, right? So, well, I will use the stress. This is just for your information. I will use the stress, but in order to check how to formulate the work, so stress is a force divided by area. So in order to convert this to the work, so you need to times the volume. So you will get the force times the distance will be the work. So the stress times the volume. So the stress times the volume is the average atomic volume, omega. So that will be much easier to remember. You don't need, this is, in order to have this concept, that's much easier to remember. Should be the stress times the average atomic volume. So you got the area volume. So you have a distance, force distance. You got the work. Okay. So some people, as long as you write this down, so some people use the other point of view to interpret this term. They also call it as, we also visualize the stress gradient. This is stress gradient. So stress gradient times the average atomic volume serving as a driving force also works. So you have two different approaches to formulate this driving force induced by the stress field. So this is there are two possible driving force acting on to induce the atomic flux here. But the ideal way is we don't want to have the atomic flux, right? Because as long as you have this one, you will visualize the extrusion and void formation. So this should be equals to 0. When it reach quasi steady state, we hope this equals to 0, so we can find the LC. So this equals to 0, so equals to 0. So you move this turn to right-handed side. So I can get the critical product. Because you move this equals to 0, so you delete this identical, I mean the same term here. So after arrangement, you can get this equals to this. And E, I use the current density divided by electrical conductivity to replace the electrical field. Okay, if you take a look What's the dx? Dx is the LC you are interested in because ds is the stress gradient. So I arrange them. So I move the delta x to with the current density and move the material part to Galveston. So what we have here is we have critical product, which is the current density times the LC equals to the right-handed side. What we have here is a stress, average atomic volume, beta, and also the electrical conductivity. If you take a look on this term, for a designer or for some people want to design the length of conducting wire, usually they already know the required current density for this chip. So this be fixed. Current density fixed depending on the chip design. And this is as long as you choose or what type or what kind of conducting line you are going to choose. This is the right-handed side is materials dependence, right? Copper have its own average atomic volume, beta, and also conductivity, and also this stress field. Stress field actually usually to represent the sigma. Usually we use the yield strength to represent that because higher, well, as long as the stress higher than yield strength, the system will reach, will cause the permanent plastic deformation. 所以通常这里 sigma 我们会带的是 yield strength，因为当你的应力超过 yield strength 的时候，这个系统这个材料就会达到永久的形变，所以就是很典型的 extrusion 这个例子。所以右边这里是材料的特性，然后左边是 current density。通常每一个，当你在 chip，你有几个 chip 在那个 substrate 上的时候，在 silicon substrate 上的时候，你就已经决定了你的 current density 要是多少。所以 as long as你知道你要哪一种材料作为你的导线，然后你又确定了 current density，you can for sure you can get the critical line length for conducting wire。OK，所以就在这里的话，你就可以算出一个最安全的，你拉线现场的，就那个导线的长度，然后不会伪造 EM induced damage，OK 吗？好，然后从这里你也可以有一个就是 the other idea，就是EM 有没有人可以阻挡 EM？有 stress field，它是拿来阻挡 EM 的，有机会来阻挡 EM，好吧？This is a primary effect. And we also have, in the meantime, we also have secondary effect of electromigration. People call them as current crowding. Induced by we have a non-uniform distribution of current density throughout our conducting wire or conducting line. So I grabbed the figures here. We also, here in this case, we have a titanium nitride. On the top of it, we have alumina serving as the conducting wire. We have anode here, cathode at your left-handed side. So as long as you apply the current passing through left-handed side, which also implies that the electrons move to right-handed side, right? And that will have chance to push the atomic flow or alumina flow move to right-handed side. And in the beginning, probably you can visualize this alumina atom accumulation at this bottom right region that will cause the stress gradient. And this is atomic flux, right? But in the meantime, we know that the vacancy flux, major primary vacancy flux will go to opposite directions, will be go here. But what's the secondary effect is due to we have a non-uniform distribution of current density. So people use the simulation technique to plot the distribution for current density for this alumina wire, and they visualize the light gray region have a higher current density, and at your upper left corner have a lowest current density. So we visualize the gradient for this current density. So the vacancy, some part of vacancy will move toward or along with this current density gradient. The gradient for this current density will move to these directions. So this is we call the secondary effect of electron migration, current crowding. So in some case, you also will visualize the void formation at some region with lowest current density. This is we call the current crowding effect, which is a secondary effect of electron migration. But some people probably will further ask, why, Professor? You can interpret this vacancy for electrons flow. Actually, if you have vacancy, lots of vacancy here, it will impede the electrons flow, which means that the electrons, when electrons flow to right-handed side, it will push the vacancy, right? Because vacancy, if you have a vacancy, that will increase the resistivity. So electron don't like it, they will push it. So always push it, they will move somewhere, and somewhere to where actually is a gradient of the current density. Okay, but major, the primary vacancy flux also go this way. Just some of the vacancy flux will move along the gradient of current density to this region. So are there any evidence demonstrate this? Yes, yes. So I can show you here. If you move to this slide, uh, look carefully for this region. Actually, the electrons flow is go to left-handed side, go up and go to left-handed side. So this is a major, I mean, higher current density region. But you did visualize some void formation, right? But at lower current density region, we also visualize the void formation. So this is, you can write down, this is a secondary effect. We call the current crowding effect. So this is evidence demonstrate that.